Hey, everybody. It's Wednesday, May 26th. And as you can see here in the aim today, our goal for today's video is all about how we can use the features of a periodic wave to determine an equation for the speed of the wave. Now, really what we're doing today is picking up the conversation that we started last week and continued up to Monday. Now, obviously, yesterday was the circuits exam. Hopefully, you had a pretty decent time with that. If you remember back to last week, though, we started to talk about waves, and we talked about very basic information having to do with waves. We talked about the different types of waves, the difference between a pulse and a periodic wave, different types of periodic waves like transverse waves and longitudinal waves, the fact that waves transmit energy without transmitting matter. And then we eventually got to the characteristics and features of a periodic wave. And this stuff is really, really important because all periodic waves possess those four features and characteristics. All periodic waves have a period, a frequency, an amplitude, and a wavelength. And so because all periodic waves are in possession of those characteristics, they're very important for us to discuss. Now, I hope what you've realized about this whole course thus far is that it follows a sort of logical progression in the sense that everything builds on everything else. And so now that understanding of the entire year's worth of the course has culminated in this final unit here that we're going to discuss, which is waves. But it's important to realize that that's also actually been happening within this course as well. In the beginning of the year, we started to talk about like really basic measurement stuff like the metric system and how we can measure various quantities. And then we talked about distance and displacement, ultimately to then talk about things like speed and velocity. And that's really what we're getting to here. Implicit in everything we've said so far this year, like specifically the point that a wave transmits energy, is that it moves from one point to another point. And so it should be pretty clear to everybody that if a wave moves from one point to another point, it definitely has a speed. And so the first and most obvious question we want to ask here is, well, how do we determine the speed of a wave? And the answer to this question is probably not going to be all that surprising. We determine the speed of the wave the way we determine the speed of literally anything, which is to use the equation v equals d over t. However, there's a little bit of complication here. And that's because, number one, some waves are not visible to the human eye, like radio waves or microwaves or X-rays, not visible to the human eye. Other waves just travel incredibly fast. Some waves travel incredibly fast and are invisible to the human eye. And so with all of these complications, it's going to be really difficult for us to directly measure distance and time if we can't see the thing that's traveling this distance that we're trying to measure. And so what we're going to say here, more importantly, is that since we have described various characteristics and features of periodic waves, it would be ideal if we can come up with an equation for the speed of a wave in terms of the natural characteristics of a wave. We talked about frequency, we talked about period, we talked about amplitude, we talked about wavelength. And so it's going to be really nice if we can come up with an equation for the speed of a wave that is written in terms of those features. Take a second to pause this video here and write that down. And when you hit play, we'll talk a little more about how we can do that. Now, very quickly here, before we really get into detail about how we can measure the speed of a wave, you really just need to keep in the back of your mind here that the main requirement for any equation for the speed of a wave is that it has to end up with units of speed, specifically with units of meters per second. It should be pretty clear to everybody that that is going to be a pretty obvious requirement for wave speed and for a wave speed equation. If we try to come up with an equation for wave speed and it gives us units for meters, well, that's just not an equation for speed. And that's a really important thing to realize. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at that simulator that we showed a couple of times over the past few days. All right, so let's take a look at this simulator here. We've looked at this a lot over the course of the last bunch of days here. So we can get a wave going here, just give it some random frequency here, and now we see the wave traveling. And as I mentioned here, while it is a really nice thing for us to do to be able to sort of come up with an equation for the speed of a wave in terms of the wave's natural characteristics, we should probably think about this in terms of general motion ideas in general. I want you to follow that point. Notice here that point is directly at the peak of this wave. And I want you to notice that the peak of this wave is exactly at this grid space. You know what? I'm actually going to go ahead and mark this grid space here so we can just keep our eye on it. Now, we're going to set this thing in motion here, and I want you to keep an eye on this peak as well as this point in particular. So notice here, this peak is now traveling. This point is going all the way down, and now it's coming all the way back up to its maximum positive displacement again. And notice now that this point has reached the place where it originally was, when it's reached its initial position, the peak that we were originally tracking is over here. And so here's the point. While we would ultimately like an equation for the wave speed that is simply written in terms of various features of the wave, what we just saw is a basic distance over time problem. The peak of this wave has traveled this distance in an amount of time that was needed for this point to complete one full cycle, to start here at the top, to go all the way down, and to come back up again. In case you missed that, I want to run that one more time. Watch this point. It's going down. This peak is coming over. Watch that. Look at the point here. Now it's starting to come back up. This peak is still going over. The point is up, and here we go. And this peak has made it over here. Now, hopefully you realize what it is that just happened. Notice the amount of time that just passed was an amount of time required for one full cycle to happen. Do you see where we're going with this one? Once again, the amount of time that just took is the amount of time required for that point to experience one full cycle. What's that the definition of? The time required for one full cycle. That's the period. And so what it is that we're saying here, thinking about the equation V equals d over t, is that this thing just traveled this far in one period. Notice what this distance is. This distance is measured from the peak of the wave that we were following this whole time, that would be this one, to the adjacent peak. What is the distance from one peak to another peak defined as? That's defined as the wavelength. So here's the kind of thinking we engage in right here. We start with the equation V equals d over t. We acknowledge that this isn't really going to work so well for us in this kind of situation. However, if we use this simulator, we realize in one cycle that the distance traveled by the wave is equal to the wavelength. And the time it takes for this wave to travel a distance equal to the wavelength is the period. And so we can take the original just speed equation, V equals d over t, and we can plug the wavelength and the period into it. And that now is an equation that both follows the form of the equation V equals d over t and is written in terms of characteristics of the wave. Furthermore, because wavelength is measured in meters and the period, which is the time it takes to complete one full cycle, is measured in seconds, notice that equation also is in units of meters per second. And that's pretty cool. Now, I'm going to tell you right now, not to spoil this, because we are going to get to it in about 1 second, but if you go to the reference table and you look at the equation for the speed of a wave, that's not it. Speed equals wavelength over period is not in the reference table. And the reason why that equation is not in the reference table is because frequency is more common of a measurement that's given than period. And so what we would ultimately like to do is to be able to get this equation written in terms of frequency. And luckily, there's a really easy way to do that. If you look in the reference table says the period is the inverse of the frequency. And so that means if we take that equation and we solve it for frequency, we get frequency equals 1 over the period. Now, there are a number of ways you could do this. Let's actually just stick with this equation that we have here. If we take the equation V equals lambda, remember the symbol for wavelength is called lambda. If we say V is equal to lambda over the period, and we recognize that the period is 1 over the frequency, then we could substitute that in the denominator here and say the speed is the wavelength lambda divided by the inverse of the frequency. Now, of course, when you divide by a fraction, you flip and multiply. And so that means this is going to be equal to the wavelength times the frequency over 1, which is just equal to the frequency times the wavelength. And that version of the equation is definitely the most common version of the equation that we use. Now, it should be noted, and I just want to say this before we jump on to the next slide here, that even though this equation is written as frequency times wavelength, it still has units of meters per second. Frequency is measured in hertz. Wavelength is measured in meters. But what you have to remember here is that the hertz is an inverse second. And so even when we take an inverse second, or 1 over seconds, and we multiply it by a meter, we get meters times 1 over seconds, which is equal to a meter per second. No matter which way we write this wave speed equation, whether it's in terms of the wavelength and the period or the frequency and the wavelength, it works out to have units of meters per second. And that's why this equation is so valuable. It covers every single thing we said in the beginning of the year about what a speed equation should show, and it's written in terms of fundamental characteristics of a periodic wave, like its wavelength, frequency, and period. Take a second to pause this video here and write that down. And when you hit play, we'll more formally introduce these equations. All right, so I want you to write this down also under the heading wave speed, I suppose. The symbol for the speed of a wave, pretty obviously, is v. The equation here, we're going to write two ways. V equals f lambda, and I want to just point this out here. V equals lambda over the period is totally a valid way of writing down this equation. The thing that you need to know, though, is that it's not in the reference table. That's something to be careful of. However, t equals 1 over f is. And so we can say here that even though v equals f lambda is the equation written in the reference table, if you substitute in f equals 1 over t into this equation, then you get this second version of it. We should also say here that lambda is our wavelength measured in meters, f is our frequency measured in hertz, t, of course, is the period measured in seconds, and v is the wave speed measured in units of meters per second. And of course here, that unit is meters per second. One more time, I just want to show here for reference, because I think over the years, kids have gotten confused about this. V equals f lambda ends up producing units of hertz times meters. That would give you units of inverse seconds times meters, which is equal to a meter per second. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So I just want to show you very quickly before we move on. If you go to page 5 of the reference table, at the section that says waves, you will see this equation here at the top, V equals F lambda. Now, I mentioned this the other day, but I just want to point it out again. Whenever we write down the symbol for frequency, usually it is this fancy italicized F. I'm not really sure why it's actually always taken on this fancy italicized F, but that is the way you will see it in most textbooks. Of course, it is in the reference table, and so that is the way we will use it. And of course, this is the way the reference table prints the lambda, like a little more curly than I usually write it. If you just write like a backslash and then a little tail on it, that's totally fine. Well, let's go ahead and take a look at a couple of problems. Here's our first problem, a nice diagram question. And so they give us a diagram of this wave, and it says, what is the speed of the wave if the frequency is 8 hertz? Okay, pretty good question. Now, of course, we just looked at the equation for the speed of a wave, and the speed of a wave is given by the equation V equals F lambda. Pretty obviously here, they tell us the frequency is 8 hertz. The question here, though, is the wavelength of this wave 6 meters? Based on everything we said on Monday, you should be able to answer that question. I'm going to say it one more time. Is the frequency of this wave, or excuse me, is the wavelength of this wave 6 meters? The answer to that question is no. Wavelength is a measurement of the length of one cycle of the wave. And if it's easy to see how many cycles there are if you just trace this out. Here I've got one full peak and one full trough, so that's one cycle. Then I've got another full peak and a full trough, so that's 2 cycles. And I guess I'll mark my cycles with a dot here like this. And then I've got another one full peak and one full trough, and so that's 3 full cycles. Also, remember we said one full peak and one full trough tells you you've got one full cycle. So notice you can always just do this by counting peaks and counting troughs. Notice here in red, I have my peaks, and so I have 3 full peaks. I guess I'll just do blue here for the troughs, and I've got 1, 2, 3 full troughs. And so 3 full peaks and 3 full troughs means I have 3 full cycles. And so essentially what's happening here is you are being given the frequency, and you are being given enough information to be able to solve for the wavelength, and then you have to solve for the speed. So let's go ahead and do that now. The problem tells us the frequency given here is 8.0 hertz. And they do not tell us the wavelength, but that was just an ordinary length that was given, was 6.0 meters. And we were able to look at the diagram and determine that the number of cycles shown in that diagram was 3. And we're looking for the speed of the wave. Well, first, we got to find the wavelength. And so the wavelength here, as we said on Monday, is equal to the length divided by the number of cycles. It's important to remember that equation, length divided by the number of cycles, is not in the reference table. But if you ever get confused about whether the equation should be written this way or the other way around, by the other way around, I mean number of cycles on top and the length on bottom, you should remember the only possible way for this equation to give you units of meters, which the wavelength definitely should have, is if the length is in the numerator. And so it's always going to be length over the number of cycles so the units work out correctly. So we're going to take our length here, 6.0 meters, and we're going to divide by the number of cycles, which is 3. And that's going to give us a wavelength in this particular problem of 2 meters. And that's it for the wavelength portion of the calculation. Now we have enough information to be able to solve for the speed. As you saw before, the equation in the reference table for the speed is v equals f lambda. And so now all we have to do is plug in our numbers. We have the frequency of the wave was given to us in the problem as 8 hertz. The wavelength here is 2.0 meters, which we just solved for. And that means the speed of our wave here is going to be 16 meters per second. And that's it. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I just want to point out one thing very quickly before we move on to the next problem, which is you got to really pay attention when they give you these length measurements, not to get tricked into thinking that's the wavelength. Notice the first answer choice here, 48 meters per second, is what you would get if you took this 8 hertz frequency and multiplied it by the 6 meter wavelength. You have to recognize here that there are multiple cycles shown, making the wavelength only 2 meters, which is what makes the wave speed choice 2 16 meters per second. All right, let's move on to another problem here. This problem, which I actually want you to pause and try on your own, it says, in the diagram below, a water wave having a speed of 0.25 meters per second causes a cork to move up and down 4.0 times in 8.0 seconds. It then says here, what is the wavelength of the water wave? Notice this is a pretty similar question, but basically flipped around. That's really all I want to say about it before you go ahead and try this. So take a second to pause this video here. Try this one on your own. Try to come up with an answer. Try to show the work for it. And when you hit play, I'll show you exactly how that should look. So notice here, they tell us in this problem the speed of the wave. Let's just go ahead and get that down right away. The speed of the wave here is 1/4 of a meter per second, 0.25 meters per second. And they tell us the cork moves up and down 4 times in 8.0 seconds. So notice here, instead of being required to solve for the wavelength like we were in the last problem, here we have to now solve for the frequency. So they told us the number of cycles here is 4.0. It says 4.0 times. It moves up and down. And it says that that happens in a time period of 8.0 seconds. And we're being asked here for the wavelength. Now, like I said, this is basically the last problem in reverse. The first thing we have to do is we have to solve for the frequency. Now, as I mentioned, frequency equation that we're going to use here is not in the reference table, but it comes from the basic definition of frequency. Frequency is a measurement of the number of cycles per second. And so here, we're going to say that the frequency is the number of cycles divided by the number of seconds, or the time. And so now all we have to do is plug into that. We have 4.0 cycles. And remember, we're not going to write down the word cycles. That's a unitless number here. It's just 4.0. And then we're going to divide that by the time, 8.0 seconds. And when we do that, we end up getting 0.5, notice 1/seconds, which is equal to 0.5 hertz. And notice, now that we have the frequency of the wave, we're ready to go ahead and solve for the wavelength. And so we have speed equals frequency times wavelength. And so notice we're going to need to divide both sides by the frequency to solve for lambda. And so lambda here is going to be the speed over the frequency f. And so our speed here was given to us in the problem as 0.25 meters per second. And we're going to divide that by our frequency, which is 0.5 hertz. And so that means our wavelength here is just going to be 0.25 meters per second, divided by 0.5 hertz. And again, 0.25 divided by 0.5 is the same thing as 0.25 times 2, right? Dividing by half is the same thing as multiplying by 2. And so we get 0.25 times 2, and that ends up giving us a wavelength of 0.50 meters, or a half a meter. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, so notice here, that's going to go ahead and make our answer to this question, choice 4, 0.50 meters. Now, before we wrap this up for today, there's one last topic that we need to make sure we address, which is how the speed of a wave really influences the way we think about how a wave travels in space, how a wave spreads out in space, or if you remember that key piece of vocabulary from the first day, how the wave propagates. And so what I'd like to do once we cover this speed equation is really just dig into the basics of how a wave is actually generated again and how a wave moves. So let's go ahead and do that now. And so you should write this under the heading Wave Propagation Key Concepts. This goes back to something we said a number of days ago, which was what causes a wave to be generated? How are waves generated? And we said waves are generated by vibrations. And so what should make sense to everybody is that the frequency of a wave ultimately is determined by the frequency of the vibration of the source of the wave. So I'm going to show you an example here in a second, but I want you to try to visualize it in your head. Let's take the sound of my voice, for example. The reason why the sound of my voice is existing at this frequency, the frequency at which you are hearing it, which is what determines like its tone, is because of the frequency my vocal cords are vibrating at. I can change the frequency my vocal cords are vibrating at. If I make them vibrate at a lower frequency, then my voice will sound like this. And if I make them vibrate at a higher frequency, then my voice will sound like this. That's the point. Notice, in order to change the pitch of your voice, pitch is a less scientific word for frequency. In order to change the pitch or frequency of your voice, you have to sort of change the way your muscles in your throat are working. And what the changes that you are making to the way your muscles are working are accomplishing is it's making your vocal cords vibrate at different rates, a different number of cycles per second. So this is a very important thing to remember. The frequency of a wave is determined by the frequency of the vibration of the source of the wave. And a very important concept here, this part in all caps is super important. After the wave is sent out, that never changes. If you imagine like a really long slinky, if I shake it really fast so that you see a number of shakes of my hand, that's going to make the slinky shake a large number of times in a short time period. And once that travels, I can't change that. It's just going to go. Once you send out a wave, the frequency is never going to change. So if we're like standing down the block from each other and I'm yelling at you, I can't change the sound of my voice after I say the thing. It's already been said. The only thing I can do is change the sound of the next thing I'm going to say. So that's the main thing you need to remember about frequency. It's determined by the source. It doesn't change. Next thing we need to talk about is the speed of a wave. And this part is a little weird, but it's just something you absolutely have to remember. The speed of a wave is determined by one thing only, and that is the medium in which it is traveling. So, for example, if you've ever been in a pool underwater and tried to talk, you notice that your voice does not sound the same underwater as it does just like sitting in a room when your voice is traveling through air. That's because the speed at which the wave is traveling is different. So the speed of a wave is determined by the medium. What I always tell everybody, and I understand that this is silly, but what I always tell everybody to help them remember this is if the waves are in the same medium, they're going to be traveling at the same speedium. Same medium, same speedium. So the speed of a wave is determined by the medium. So now hopefully you see where we're going, putting this together. The frequency is determined by the source. The speed is determined by the medium. What's the only thing we haven't covered? It's the wavelength. And this might seem like kind of a cheap sort of cop-out here, but the fact remains, the wavelength of a wave is going to be whatever it has to be to make the equation V equals F lambda true. Ultimately, then we can think the wavelength of the wave is determined by the speed equation. So the frequency is determined by the source of the waves, the speed is determined by the medium, and the wavelength is whatever it's got to be to make that equation true. So you take that speed, which is determined by the medium, you divide it by the frequency, which is determined by the source, and you get your wavelength. Now, it's important to realize one thing here very quickly, and I guess I'll write this here just so you can see this when we're going through the demonstration here in a moment. If the equation in the reference table says V equals F lambda, and the speed is determined by the medium and the frequency is determined by the source, then solving that for wavelength actually leads us to something kind of interesting. We get lambda, the wavelength, is equal to V, the speed, over the frequency. And if we're imagining a wave in a single medium where the speed is going to be a fixed number, then we can see here that the wavelength and the frequency have an inverse relationship. So what you will notice when I show you this demonstration here is that if I change the frequency, it's not going to change the speed, even though this equation might make it look like they're directly proportional. It's only going to change the wavelength because the speed, EM, is fixed by the medium. Let's take a look at that quickly before we go. So the first fact we want to demonstrate here is that the speed of a wave is determined by the medium, which would be the slinky here, and nothing else. So notice if I send through a pulse with a relatively small amplitude or a large amplitude, they still travel at the same speed. I hope that's relatively easy to see here. But if the amplitude is small or the amplitude is large, hopefully you can see here that they're traveling at the same speed. So here, we get a little bit of interference between the ones that I'm sending and the ones that are coming back, because hopefully you can notice when I send a wave, it is reflected a little bit. And so I'm going to try to do this just by sending individual little pulses here at first. So if the pulse has a small amplitude or a large amplitude, the speed is the same. Now, as far as the relationship between the frequency and wavelength, you can tell here that the frequency is determined by the source if you just keep an eye on my hand, because my hand is the source of the waves. Notice if my hand is not vibrating, the slinky is not vibrating, and if my hand is vibrating, then the slinky is vibrating. So I want you to keep an eye on my hand. I'm going to start off with a low frequency, and I want you to look at the wavelength of the wave, and then I want you to see what happens when I start to make my hand go faster. So I got a low frequency now, and now I'm going to ramp it up. So hopefully what you saw there is that as I started to make my hand vibrate back and forth more and more and more, the frequency of the wave was getting bigger and bigger. And when the frequency of the wave got bigger and bigger, because frequency and wavelength are inversely related, inversely proportional, if the frequency goes up, the wavelength goes down. And so what you should see is more and more waves bunch up closer and closer together. We'll do it one more time. All right, guys, that's it for today. Tomorrow, we are going to take a good look into the relationship and some of the differences between the speed of light and the speed of sound. So like I said, tomorrow, this wave speed equation is not going away because some of the important types of waves, like sound and light, are waves we are going to want to use this wave speed equation for. So we will be digging back into this tomorrow in more detail, where you'll get another chance to use these equations to practice solving them with some more varied applications. All right, guys. See you tomorrow.